Welcome to section 10.5, Conditional Probability. After this lesson, you'll be able to determine whether an event is independent or dependent. You will also learn to calculate conditional probability. Example 1 is on probabilities of independent events. In this example, we will look at flipping a coin twice. We want to know what the probability is of flipping a heads the first time and flipping heads the second time. Well, I could flip heads the first time and heads the second time. That's what we want. Or I could flip heads the first time and tails the second time. Or I could flip tails the first time and tails the second time. Or I could flip tails the first time and heads the second time. And those are all the possibilities. Notice how this is related to the fundamental principle of counting. Right? I have two possibilities for my first event and two possibilities for my second event. Therefore, I have 2 times 2, or 4 possibilities altogether. So, what's the probability of flipping a coin twice and getting heads for, both times? Well, there's one event where that works out of 4 equally likely events. Therefore, I have a 1 in 4 chance of flipping heads both times. So this leads us to the definition of independence. 2 events are said to be independent if the outcome of one event does not affect the outcome of the other. In our last example, flipping a coin once doesn't change anything about how you flip it the second time. That's why those are independent events. The formula for independent probability is just this. If you have 2 independent events A and B, the probability of both A and B occurring is the probability of A times the probability of B. To contrast this, let's look at the probabilities of dependent events. Suppose you have a bag of Skittles with 5 red Skittles and 3 green Skittles. If you reach into the bag and grab a Skittle at random, then eat it, and then reach in and grab another, what's the probability of getting a green Skittle both times? Well, what's the probability of reaching in and getting a green Skittle the first time? Well, we know there are 3 green Skittles. And how many Skittles are in the bag? 8, right? 5 red and 3 green. So there's a 3 in 8 chance, or a 3/8 probability of getting a green Skittle on my first grab. Well, I eat it, right? And then I reach in and I grab another Skittle, so what's the probability of me getting a green Skittle the second time? Well, if I did get a green Skittle the first time, that means there's only 2 green Skittles left. Out of how many Skittles are left? Well, I ate one of them, so now there's only 7 Skittles in the bag. Again, I'm going to multiply these 2 probabilities together. And when I do, I get 6 out of 56, which is equal to 3 out of 28. This leads us to the definition of probabilities of dependent events. 2 events are said to be dependent if the outcome of one event directly affects the outcome of the other. In other words, in our last example, because the first time we reached into the bag, we got a green Skittle and we ate it, that changed how many green Skittles were in the bag. So that directly affected the possibility of getting a green Skittle on my second draw. The formula for dependent probability is just this. The probability of 2 dependent events A and B both occurring is the probability of A times the probability of B given that A has occurred. So note that this little slash between B and A is read the probability of B given that A has occurred. So if we look back at our last thing, the probability of getting a green Skittle the second time is different than the probability of getting a green Skittle the first time because grabbing the green Skittle the first time reduced the number of green Skittles in the bag. Let's look at our next example. You flip a coin twice. What's the probability that you will flip heads the first time or heads the second time? Or both? So I know the probability of flipping heads on the first flip is 1/2. And I know the probability of flipping heads on the second is also 1/2. So how do I deal with this? Well, when I see the word or, the first thing that I think of is what happened when we were dealing with combinations. And we said, well, if I see the word or, that means I add. But adding 1/2 and 1/2 gives me 1. And a probability of 1 means that something absolutely has to happen. So that's no good, right? Because I know that this doesn't have to happen. If I flip tails the first time and tails the second time, then I will not have flipped a heads either the first time or the second time. So this can't be right. So what's the second option? Well, what about multiplication? Well, 1/2 times 1/2, that's 1/4. That's less likely than 1/2. And that doesn't make sense either, because I know that if I flip heads the first time, that's a probability of 1/2. But I'm also giving myself an extra chance here, and maybe flipping heads the second time. So my probability shouldn't go down, it should go up. So this also makes no sense. Okay, what can we do? Well, what we're looking at here is actually an example where using the complement is a better type of solution. So my question is, what's the probability of not flipping a heads either time? Because that's really the only time when this will fail. Well, the probability of that is it's a 1/2 chance to flip a tails, and if I flip a tails the second time, then that will also be 1/2. And now this is a case where I want to flip tails both times. So we know what that is by our definition of independent probabilities. That is multiplying these things. And that does give us 1/4. But we're doing the complement here, right? We're looking at what we don't want to happen, and then we're saying, well, what's the probability of that? And then taking that probability away from 1. So 1 minus 1/4, which is 3/4. That's the probability of heads or heads. Heads on flip 1 or heads on flip 2. So it's an easy mistake to make to add those things. Don't make the mistake. It's also an easy mistake to multiply them without really understanding what that multiplication means. So don't make that mistake either. Try to reason through it. Example 4 looks at grocery shopping. Suppose you're going grocery shopping for your parents, and you're taking your 2 siblings along. The grocery list has 6 items on it. You agree with your siblings to split up and each pick up 1 item and then meet back at the cart. But unfortunately, you didn't think to divide the list up between you. So you're all just sort of going out there, picking an item off the list, grabbing it, and bringing it back. What's the probability that you come back together and all have different items? Alright, so how should we solve this problem? Let's just do this in an order. Let's say I go out first, and I pick up 1 item off the list, say cottage cheese. I don't know. The point is that no matter what item I pick, it will be unique, because I haven't looked at what other people have picked yet. So there's a 6 out of 6 possibility that the item that I pick up is going to be unique. Now, what about one of my siblings? Well, they also went out, and they just want to pick up an item that isn't the item that I picked up. So how many items are left for them to choose from? 5. Out of 6 possible items are still unique. And the final sibling has 4 out of 6 possible choices left. 6 out of 6 is 1, I don't really need that. 1 times 5 6 times 4 6, that's 20. 36ths, which is equal to 5 out of 9. Notice that this is dependent events, and they're multiplied together. My first event, there's a probability of 1, so I don't really need to multiply it through, but I did anyway. My second event, the probability is based off whether or not this person chooses the item that I chose, so these are dependent events. And then the final event here is based off the choices that myself and my sibling made. So the probability affects things. In other words, I guess what we could say here is that the probability of A and B and C is equal to the probability of A times the probability of B given A times the probability of C given B and A. Let's look at our last example. Let's just do some of these probabilities sort of out of context. In example 5a, I'd like to find the probability of A and B. If the probability of A is 0.4, and the probability of B given that A has occurred is 1/5. Okay, so well, what's the probability of A and B? That's just the probability, according to our formula, of A times the probability of B given A. That's what this guy is. Well, we know what those are. We were told what they are. It's 0.4 times 1/5. If I put 1/5 into a calculator, and go ahead and do that, I get 0.2. What is that? That's equal to 0.08. Here's another one. Find the probability of A and B and C if A, B, and C are independent events and these conditions hold. Okay, well, independent events, that means I don't have to worry about the probability of B given A and the probability of C given B and all that stuff. I know that these events don't affect one another. So that really, literally just means I multiply the probability of A times the probability of B times the probability of C. I'm done. So that's 0.9 times 1, and I'm going to multiply that by 1/3, which is really just dividing this by 3, and that gives me 0.3. Well, that's everything. So you have learned in this video to determine whether an event is independent or dependent, and to calculate conditional probability. So the main things, again, are to look at whether or not the outcome of one event affects the other. If one outcome affects the other, then those two events are dependent, whereas if they do not affect one another, they are independent. Conditional probability simply reassesses the probability of a second event based on what happened in the first event. We'll talk more about this in class tomorrow. Have a good night.